Welcome to Amazing Space, your guide to the cosmos. Today we're diving into one of the most intriguing mysteries in modern astronomy, the Hubble Tension. The universe is expanding, and that fact has been known for nearly a century. However, a puzzling discrepancy has emerged when comparing different methods of measuring how fast it is expanding. This discrepancy is known as the Hubble Tension, and it has thrown cosmologists into a whirlwind of debate. Some believe the disagreement can be resolved with better data, while others suspect it hints at unknown physics lurking beyond the current cosmological models. Recent measurements highlighted in a new report have brought this so-called crisis back into focus, suggesting that the universe may be racing away faster than theory would predict. Understanding why these measurements disagree could reshape fundamental ideas about matter, dark energy, and even the eventual fate of the cosmos. So, central to the controversy is the Hubble Constant, a value that describes the universe's rate of expansion in kilometers per second per megaparsec. A megaparsec is an astronomical unit of distance, equal to roughly 3.26 million light-years. This constant might sound obscure, but it is one of the cornerstones of modern cosmology. A precise value helps determine fundamental properties like the age of the universe and the density of different cosmic ingredients, including dark matter and dark energy. The disagreement is straightforward on the surface. One method, which relies on measurements of the cosmic microwave background from telescopes such as the Planck satellite, yields a value near 67 kilometers per second per megaparsec. Another method, known as the distance ladder, uses observations of relatively nearby cosmic objects to measure how quickly galaxies are receding, producing a figure closer to 73 or 74. Although both methods are carefully refined, their results do not overlap within the margins of error, giving rise to the Hubble tension. The distance ladder technique involves gauging distances to closer cosmic objects, then building out to ever farther realms. In practice, a class of pulsating stars called Cepheid variables is used first. Their regular brightness variations indicate their intrinsic luminosity. By comparing expected brightness with observed brightness, distances can be inferred. These local measurements get calibrated further out using Type Ia supernovae, which serve as additional standard candles because they tend to explode with a predictable luminosity. As a result, astronomers can see how quickly these supernova-hosting galaxies move away due to cosmic expansion. By contrast, the CMB-based approach takes a more indirect route. The CMB is the faint afterglow left over from the Big Bang, and its temperature fluctuations encode detailed information about the early universe's composition and geometry. When fed into a cosmological model known as lambda cold dark matter, the data offers predictions for how the universe should expand over time. This model works astonishingly well for many observations, but it yields a Hubble constant around 67, noticeably lower than the distance ladder measurements. The difference is small in absolute terms, yet statistically significant, pointing to a gap that is not easily dismissed as a mere fluke. In the grand scheme of cosmic measurements, a difference of a few kilometers per second per megaparsec might appear minor. However, the two methods are so precise that the mismatch signals a potential flaw in current understanding. If the tension cannot be blamed on errors in data collection or analysis, it may be evidence that something is missing from the standard cosmological model. Possibilities range from new categories of subatomic particles, sometimes referred to as sterile neutrinos, to a time-varying form of dark energy. Another possibility is that dark matter behaves differently than assumed. Any of these scenarios would make the cosmos expand at a rate not predicted by existing models. The Hubble tension also poses practical implications for predictions about how quickly galaxies form, how large-scale structures evolve, and even whether the universe will continue expanding forever or might eventually slow down. The article points to newly refined techniques for measuring cosmic expansion. Observations from the Hubble Space Telescope and ground-based telescopes have improved the distance ladder approach, reducing systematic uncertainties in calibrating Cepheid stars and supernova distances. On the other side, experts analyzing CMB data have attempted to account for any possible bias or overlooked factor that might artificially lower the expansion rate. Yet, the discrepancy persists, suggesting that the mismatch cannot be trivially explained by measurement errors alone. One pivotal development lies in using alternative rungs on the distance ladder. For instance, red giant stars have a well-defined tip in their luminosity curve, which can serve as another standard candle. Multiple approaches, each using distinct calibrators, now converge on a higher Hubble constant, around 72 to 74. These findings intensify the sense that there may be deeper theoretical reasons for the mismatch. Researchers have also explored other independent methods to cross-check these conflicting values. Gravitational lensing, for example, measures how light bends around massive foreground objects. By gauging the time delays in signals from distant quasars, astronomers can infer the Hubble constant in a way that is entirely independent of key feeds or the CMB. While early results from lensing have sometimes hovered between the two major values, recent improvements often align more closely with the local distance ladder measurements. Efforts to measure cosmic expansion using gravitational wave events, dubbed standard sirens, also present a promising new frontier. When neutron stars collide, they send out ripples in spacetime that can be measured by facilities like LIGO and Virgo. These signals may potentially provide a fresh measurement of cosmic expansion if astronomers can identify the host galaxy of the gravitational wave event. However, the data remain limited for now, and achieving the precision needed to settle the Hubble tension will likely require years of observations. Some theories suggest a hidden component to dark energy, or that it changes over time in ways not predicted by lambda cold dark matter. Others speculate there might be new fundamental particles that alter the physics of the early universe, speeding up expansion at specific epochs. Still, another route involves early dark energy, an additional ingredient that may have temporarily influenced the growth of structures before decaying or transitioning into something else. Each hypothesis carries pros and cons. Introducing extra complexity might help explain the Hubble tension, but any modification must also match other precise observations, such as the cosmic abundance of elements like helium and lithium. Cosmologists typically subject these alternative models to intense scrutiny, aiming to maintain consistency with data from gravitational lensing, large-scale galaxy surveys, and more. Finding a single solution that neatly resolves the tension and remains consistent with all known observations is a formidable challenge. Future missions and experiments are poised to shed more light on this cosmic mystery. Space-based observatories such as the Nancy Grace Roman Space Telescope and the European Space Agency's Euclid mission will map billions of galaxies with unprecedented precision. Scientists hope these missions will tighten constraints on the Hubble constant or reveal new cosmic parameters that modify current models. Greater precision is also expected from next-generation ground-based facilities like the Extremely Large Telescope and the 30-meter telescope. By cataloging more Cepheids, supernovae, and gravitational lens systems, astronomers plan to refine expansion rate measurements further. Meanwhile, advanced analyses of the CMB using improved detectors that capture polarization signals may reduce potential uncertainties in the early universe method. If the tension persists through this flood of new data, a revolution in cosmology may well be on the horizon. The key takeaway from this article is the Hubble tension is more than a mere technical squabble. It strikes at the heart of how cosmic distances, timescales, and physical laws are understood. The ongoing mismatch between measurements of the local universe and insights from the early universe has spurred a flurry of theoretical and observational research. Whether the solution lies in refining measurement techniques or rewriting parts of the cosmological model remains an open question. What is clear is that the cosmos is not short on surprises. Where once the primary debate was whether the universe's expansion rate was around 67 or 73, the conversation has broadened to a deeper question. Could the universe be governed by physical processes yet to be discovered? The resolution of the Hubble tension may come gradually, through a confluence of new data, advanced telescopes, and bold theoretical innovations. As each new study emerges, it brings the cosmic puzzle into sharper view, illuminating pathways to answers that might, in turn, reshape modern astronomy and physics. In that sense, the crisis is also an opportunity. By recognizing what does not fit, a doorway opens to hidden chapters in the story of the universe, waiting to be revealed by the next generation of observations.